You are about to step into a mystery where science meets the unknown. Imagine a chandelier of gold and braided wires descending into a vat colder than deep space. At the bottom, a fingernail-sized chip waits in a hush so complete that one stray photon would be a shout. A scientist taps a keyboard. Invisible waves ripple through superconducting loops or laser-trapped atoms. A coin is coaxed to be both heads and tails, and 1,000 mutually exclusive possibilities begin to interfere like tides crossing in moonlight. If it works, this machine won't grind through options one after another. It will choreograph them all at once, letting wrong answers cancel and right ones crescendo. In that moment, it feels as if logic itself were a physical substance we can bend. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Because tonight we're traveling into the quantum computer mystery. Machines that some fear could crack our cryptography, and others hope will design medicines and materials we can barely imagine. Devices that might not literally rewrite reality, but could rewrite what reality lets us do. The modern origin story begins as a discomfort. In the 1980s, physicists realized that simulating quantum mechanics on ordinary computers explodes in difficulty. Double the number of particles in the space of possibility squares, then squares again. Nature, meanwhile, simulates itself effortlessly. A provocative question followed. If the world is quantum, why not make our computers quantum too? Early pioneers sketched the rules. A quantum bit, or qubit, is not 0 or 1, but a superposition. Entanglement links qubits so that the whole carries information the parts do not. And quantum gates, precise pulses and interactions, steer amplitudes so that when you finally measure, interference nudges you toward a useful answer. For a while, this was elegant armchair engineering, until 2 algorithms jolted everyone awake. One showed how a quantum computer could factor large integers efficiently, undermining the RSA and elliptic curve schemes that guard banking, diplomacy, and the everyday web. Another showed how to search an unstructured list in roughly the square root of the time a classical machine needs. A modest speed-up that becomes a thunderclap when the list is astronomical. Suddenly, quantum computer wasn't just a physics toy. It was a technology with geopolitical implications. Building one turned out to be like tuning a violin during an earthquake. Qubits, whether carved into superconducting circuits, levitated as ions in vacuum, marshaled as neutral atoms held in optical tweezers, or guided as single photons, must be isolated from the heat and noise of the world, while remaining exquisitely controllable. Every interaction with the environment leaks information. Every leak collapses the delicate superposition you worked so hard to create. This fragility is the dragon at the gate. The field's answer is error correction. Encode one logical qubit into many physical qubits, detect tiny mistakes without learning the answer, and repair them on the fly. It's ingenious, but costly. To run a long, fault-tolerant computation, you may need thousands of physical qubits for each logical one, plus constant housekeeping that itself must be nearly flawless. The path from a lab demo to a useful, stable, general-purpose quantum computer is not a sprint. It's a siege. And yet, piece by piece, the siege makes ground. Quantum devices have executed small instances of algorithms that were once purely theoretical. They have performed quantum simulations of simple molecules and exotic phases of matter, offering a preview of how chemistry might feel when the computer speaks the same language as the molecule. Teams have shown error-corrected operations on a few logical qubits, proving that the concept is more than chalk on a board. Others have demonstrated quantum advantage. Tasks contrived to be easier for a quantum device than for any classical competitor, if only by a nose. Each step brings celebration and skepticism in equal measure, because the benchmark that matters is not whether a quantum device can do something hard, but whether it can do something hard and useful that a classical machine cannot catch up to with clever tricks. To see why quantum computing is not just fast computing in disguise, imagine a vast concert hall of possibilities. A classical algorithm sends one soloist down one aisle at a time asking, "Is this the seat we want?" A quantum algorithm sends a chorus through every aisle simultaneously, allowing their voices to interfere. By arranging the notes, quantum gates, you make the wrong paths sing out of phase and cancel, while the path to the solution resonates. When you listen, measure, you hear the loudest answers most often. This is not magic. It is physics exploited as calculus. But the same physics that grants you the chorus punishes you for sloppiness. If the singers drift off pitch, if noise smears the phases, the cancellation fails and the performance collapses into cacophony. What, then, could these machines actually change? 3 frontiers stand out. First, quantum simulation, using qubits to emulate molecules, materials, and quantum fields. We could explore catalysts atom by atom, design nitrogen-fixing pathways that sip energy compared to today's industrial behemoths, discover high-temperature superconductors for lossless power, or model protein folding and drug binding beyond the reach of current brute force. Second, optimization and sampling, finding good solutions in labyrinths of possibilities, routes, schedules, portfolio hedges, or the parameters of a machine learning model. Here the gains are subtler. Many flashy claims have softened under scrutiny. Quantum annealers and near-term algorithms can help, but they do not wave a wand over NP-complete monsters. The best use cases blend quantum with classical and hybrid loops, where quantum subroutines provide high-quality samples or gradients that accelerate a classical outer loop. Third, cryptography and the infrastructure of trust. Shor's algorithm breaks today's public key cryptography in principle. Even if large fault-tolerant machines are years away, adversaries can harvest encrypted traffic now and decrypt it later. That is why governments and companies are migrating to post-quantum schemes designed to resist both classical and quantum attacks. Meanwhile, quantum itself offers new tools. Quantum key distribution can detect eavesdropping by the way measurement disturbs the system, and quantum secure randomness can be certified by loophole-free tests of entanglement. So where does the rewrite reality headline come from? Partly from the giddy sense that a computer which choreographs probability could tilt the possible. A quantum device won't change the past or conjure gold from air, but it can turn the knobs on discovery, making some inventions cheap that were once prohibitively expensive in time and energy. If you can simulate a catalyst instead of guessing and testing for years, you have rewritten the path to that chemical reaction. If you can sample the rare, crucial tail events in a complex system more efficiently than chance allows, you have rewritten how we predict risk. The machine doesn't bend reality. It bends the cost function that decides which realities we can build. There are, however, deep reasons to temper both doom and hype. Complexity theory, the mathematics of what is hard, draws boundaries around quantum advantage. The class of problems believed to be efficiently solvable by quantum computers, BQP, is powerful but not omnipotent. NP-complete problems are unlikely to yield in general. Many claims of sweeping speed-ups for machine learning or optimization have retreated as classical algorithms improved, or as overheads were counted honestly. On the flip side, classical simulation also has limits. Clever tensor networks can mimic certain quantum systems up to a point, but not beyond. Error mitigation techniques can squeeze more from today's noisy chips, but they cannot replace full error correction for very long computations. The frontier is a moving target, with both camps learning from each other. The hardest part may not be physics, but engineering at absurd scale. To simulate a pharmacopoeia or break global cryptography, we need millions of physical qubits operating with fault-tolerant precision, bathed in cryogenic stillness, fed by mile-long looms of microwave lines or lasers, and orchestrated by control electronics that themselves barely know warmth. We must fabricate qubits uniform enough to tile like bricks, and quiet enough to hold a phase for thousands of operations. We must build compilers that translate human intent into pulses resilient to drift and crosstalk, and error-correcting codes with thresholds high enough to be practical. We need supply chains for dilution refrigerators and cryo-CMOS chips, and software stacks that make quantum programming less like surgery and more like art. None of this is easy. All of it is happening. Beyond the pragmatic horizon lies a speculative one worth exploring with open eyes. Some researchers are using small quantum processors as laboratories for ideas in high-energy physics, mimicking toy models of wormholes, thermalization, and scrambling to probe how information behaves in extreme settings. Others envision a quantum internet, where entanglement distributed across cities enables secure communication and networked sensors whose precision scales beyond classical limits. There are dreams of programmable matter, where arrays of neutral atoms or spins realize exotic phases on demand, of clocks so accurate that they map gravitational potential across a city block, of cameras that image light, that never touches the object. None of these demands a science fiction leap. They demand persistence in mastering entanglement as a resource, the way we once mastered steam, electricity, and bits. Of course, mystery attracts myths. One says a quantum computer explores parallel universes and plucks the answer from the best one. Metaphor aside, the machine explores amplitudes in one world, using interference right here to steer outcomes. Multiple universes are not required. Another says quantum will make AI omniscient. In truth, some subroutines like sampling from complex distributions or solving certain linear systems might see gains, but learning from data remains constrained by noise, bias, and the stubbornness of reality. A third myth promises instant code-breaking doom. The threat is real enough to force cryptographic migration, but it is not a lights-out switch. It is a clock with years on it, and we are already replacing the locks. There is a quieter philosophical undercurrent to all this. The classical computer taught us that logic can be embodied, that thought can be engineered. The quantum computer, if we learn to build it at scale, will teach us that interference and entanglement, features once exiled to chalkboards and thought experiments, can be engineered too. That has consequences not just for technology, but for worldview. It suggests that information is not an abstract bookkeeping device layered on top of matter. It is a physical commodity with costs, symmetries, and conservation laws. It suggests that computation is not just something we do inside machines. It is what physical systems do when left to themselves. In that light, a quantum computer doesn't rewrite reality. It speaks in the dialect reality already uses, And yet, there is an existential tremor when you stand beside a dilution refrigerator and hear it breathe. If a machine can exploit the way the world superposes possibilities to crack problems that defied us for a century, what else does that say about the world? Does it make the universe more comprehensible or more alien? Perhaps both. Comprehensible because we can bottle strangeness and make it work. Alien because success has a price. The humility to accept that the fundamental currency of prediction is probability amplitudes, not certainties. We will become more comfortable living with devices whose intermediate states cannot be described without complex numbers, and whose inner workings are literally closed to view until the end. That is a cultural as well as a scientific shift. Pragmatically, the coming decade looks less like a singularity and more like a braid. One strand is cryptography's renovation. Governments adopting quantum-resistant standards. Companies auditing long-lived data. A harvest now, decrypt later mindset making the present urgent. Another strand is chemistry and materials. Early quantum-enhanced simulations, validated against experiment, creeping from toy molecules toward catalysts and battery components that matter. A third is sensing and networks. Entanglement-assisted devices measuring time, fields, and motion with startling finesse. Quantum repeaters knitting islands of coherence into continental webs. Meanwhile, classical computing keeps racing, specialized accelerators, smarter algorithms, reminding us that quantum is not a replacement for the digital world, but an instrument to add to its orchestra. If there is a single sentence that captures the mystery, it is this: quantum computers are not powerful because they compute more. They are powerful because they compute differently. The bet we are making, as a species, is that differently opens doors we could not pry with brute force. We might be wrong about some doors and astonished by others. That is how exploration works. So let the camera return to that chandelier in its cold cathedral. Picture the pulse sequences flowing like music down coaxial cables. The qubits precessing like compass needles in a hidden wind. The error-correcting code murmuring and mending as it goes. Somewhere in that choreography, a cancellation sharp as a blade leaves only the narrow path to the answer standing. When the measurement lands, a single classical bit splashes back into our world. 0 or 1. The end of a long quantum sentence we cannot read, but can design. If we get good at writing those sentences, at asking the kinds of questions that interference can answer, the phrase rewrite reality will stop sounding like a boast and start sounding like a responsibility. We will choose which problems become cheap, which secrets become obsolete, which materials become commonplace. That is not a power to fear or worship. It is a chance to aim our curiosity with precision. So I'll leave you with a question to carry into the comments. If you could give a fault-tolerant quantum computer its first truly world-changing task, would you point it at chemistry, climate, medicine, security, or something stranger? And how would you know that the answer it brings back is the kind of reality you want to help write?